So we are glad to have Professor William Kinney give the lectures on inflation at this school. Will is a professor of physics at the State University of New York at Buffalo. He has worked extensively on a variety of aspects of inflation, ranging from models with large eta, some of which he will talk about, comparing models of inflation with the cosmological data, and the issue of the Trans-Planckian problem in inflation. Over to you, Will.
Okay, thank you. I'm very grateful for the invitation, and it's a pleasure to be here even virtually. I want to say I'm really sorry I can't be there in person, because I know that really the heart and soul of a school like this is a lot of the informal interaction that happens outside of lectures. And I think it's unfortunate that we won't have that opportunity. But we will make the best of it. And so let's dive right in. This is a sort of an outline of the 4 lectures that I'm planning on giving, give or take. So time permitting, we're going to cover basics of inflation. That's what we're going to be talking about today. Basic background dynamics, how it fits into the larger picture of cosmology. The second lecture will be diving in a lot of detail into perturbations in inflation. And I know that this is nice because David Wands is covering a lot of the general relativistic perturbation theory in detail, which frees me up to just sort of write down some of the results and talk about how it fits into inflationary spacetimes. And in particular, I want to do a little bit of focusing on the horizon crossing formalism in slow roll inflation, because then in the third lecture, when we start talking about non-slow roll models, we'll be looking at this sort of widely used formalism for calculating density perturbations in more detail, and in particular the places where it breaks down. So in the third lecture, we're going to be looking at non-slow roll models, and in particular the limit of ultra slow roll inflation and its more general cousin, the constant roll inflation models, talking about how these fit into the sort of standard approximations and the standard formalisms that we use and how it breaks them. And in particular, I want to talk about aspects of attractor behavior in these solutions. One of the things about ultra slow roll and constant roll inflation is that there's actually a lot of stuff in the literature out there that's wrong. And one of my goals here in these lectures is to clear up some common misconceptions about these models. And finally, the fourth lecture will be diving into issues related to quantum gravity. So in particular, the idea of eternal inflation and the inflationary multiverse, and also talking about inflation in the context of a lot of these new ideas in string theory relating to the swampland and how inflation fits into these things. That's the basic plan. So let's get started. So let's talk about basics of inflation and cosmological spacetimes, right? So you're familiar with the metric from special relativity, right? This idea that we have space-time and the length element in space-time is given by dt squared minus dx squared, which creates this very familiar causal structure of the light cone in a Minkowski space-time, where in fact you have the your causal future is located inside your future light cone. Your causal past is located inside the past light cone. That is, if we are sitting here at some event in space and time, right? An event is just a point in space and time. So if we're here, our causal future lies inside the light cone, where light in this, in the correct units travels in space-time at 45-degree angles. So anything that comes from, that starts out at our location in space-time and goes out to somewhere like this, you'd have to travel faster than the speed of light to get out to that point. So causal future is inside the future light cone, causal past is inside the past light cone, and then all of the other regions that are causally disconnected from this event P are labeled elsewhere. And in a sense, this region elsewhere relative to a point in space-time is the simplest example of what we mean when we talk about in relativity of what we mean by sort of effectively a separate universe. All of these points are causally disconnected from this particular point in space-time here. They're not causally disconnected from all the points in the causal future of P, for example, so this is almost sort of a trivial sense of what we mean by a different universe. We'll be talking about more sophisticated examples of this where they're really separated by horizons and so on later on, in particular in the fourth lecture. So how do we generalize this to cosmological spacetimes? And So in order to introduce cosmological expansion, in order to generalize this simple Minkowski picture to a Robertson-Walker spacetime, what we do is we add time dependence to it. Before I leave this slide, I want to emphasize that one of the characteristics of this Minkowski light cone structure is that both these future and past light cones extend infinitely forward in time and infinitely backward in time. Minkowski space is what's called geodesically complete. It has no initial surface, no boundary at finite past time or finite future time, or a final surface at finite future time. Robertson-Walker spaces, of course, are going to break this. So in order to generalize this to cosmological spacetimes with dynamics, what we do is we add time dependence to our spatial coordinates. So we add a time-dependent scale factor A that is multiplying our spatial scales in such a way as to introduce the concept of expansion. Right. So this results in the case of a flat cosmology, this very familiar idea of that we have, for example, a nice analogy for a flat cosmology would be an infinitely large grid of squares. So we take a grid of exactly identical squares. We imagine that grid extending off infinitely in all directions. And then expansion, this increase in the scale factor, is simply the idea that these squares get larger and larger in size with time. And as time progresses, these squares get bigger and bigger and bigger. But notice that this space satisfies the cosmological principle, the idea that there's no preferred position in the universe, because every square is identical to every other square. There is no center to the expansion. There's no edge to the space since it's infinite. It is perfectly homogeneous and isotropic. Now, I'm assuming this is all familiar to everyone in the audience. If we take this and plug this scale factor into the Einstein field equations for general relativity, and we'll see the particular solutions in a moment, what we find is that if we turn the clock backward, if we go backward in time, as we go back in time earlier and earlier in the universe, these squares were smaller and smaller, everything in the universe was closer and closer together. Eventually, at some finite past time, we see that these squares all contract to zero size. This is the moment of the Big Bang, the initial singularity. So unlike the spacetime of special relativity, which is infinite in time, both forward into the future and into the past, the Robertson-Walker spacetime is infinite into the future, but it is actually finite, past finite. And one way we can see this, we can draw an analog of the spacetime diagram that we did for Minkowski space by doing a trick. We can redefine our clock, redefine the way we measure time to use a clock that slows down with the expansion of the universe. Such a clock is called conformal time. And in the language of the metric, what we do is we simply factor that scale factor out into an overall conformal factor, multiplying an effectively Minkowski metric. So now what we have in conformal units is we simply have a Minkowski spacetime multiplied by an overall time-dependent conformal factor. And this conformal time tau will figure very prominently, especially when we talk about inflationary cosmology. So in this case, we can draw, since light travels on geodesics of zero proper length, that is, light travels on geodesic where this ds squared is equal to 0, just like in Minkowski space, we can draw the causal structure of a Robertson-Walker spacetime by drawing light cones where the light travels at 45 degrees in these conformal coordinates. So the difference between a Robertson-Walker spacetime in this coordinate system and a Minkowski spacetime, locally they're identical, but globally they're different because the Robertson-Walker spacetime, unlike the Minkowski spacetime, is past finite. In fact, our past light cone does not extend forever into the past. It actually extends a finite amount of time, even in conformal units. And what you find is that now a Robertson-Walker spacetime is a Minkowski space, except in conformal units, except with the past light cone chopped off at some finite past time. And this surface, this initial surface that chops off our past light cone in Minkowski space, is the Big Bang singularity. So this is, I mean, you're probably familiar with the misconception that many people have of the Big Bang being an explosion that happened at some point in space and everything flew outward from it. In this picture, we see very clearly in this structure that the Big Bang actually happens everywhere in an infinitely large space at once. So in the standard, radiation-dominated hot Big Bang model that predated the inflationary model, an infinite hot absolutely homogeneous and isotropic universe pop into existence all at once out of an initial singularity, which is this initial surface of the Big Bang that happened at finite past time in cosmology. And one of the interesting questions we want to ask about inflationary cosmology, or about any alternative or extension to the Robertson-Walker space, is, can we get rid of this initial singularity, or is it somehow inevitably always still there? And I hope to have time to have some comments on that at the end of the very last lecture, to talk about this concept of geodesic completeness and how it applies to inflation, maybe even talk a little bit about some recent work we've done on bouncing models and geodesic completeness. So how do we make this quantitative? This is the basic structural picture. Is now we have a causal structure with our past light cone finite and our future light cone infinite. Our past light cone is chopped off by this initial surface of the Big Bang. So let's look at this in a mathematical sense. So if we take this metric that we have defined, so this is our Robertson-Walker metric. This can be either flat or curved at this point. I'm saying this line element here can also include curvature. So I haven't specialized yet to the, well, in this case, I actually have written down a flat space version of this. So in the flat Robertson-Walker space, which is sort of the three-dimensional generalization of this even infinite grid of squares, in 3 dimension, we have an even and infinite lattice of cubes, and all of the cubes are getting bigger and bigger and bigger with time. And if we plug this into the Einstein field equation, in the case of a flat cosmology, I'll show the non-flat version of this equation in a future slide. What we find is we can define an expansion rate that is the logarithmic time derivative of the scale factor squared, or that is the Hubble parameter, right? This is the expansion parameter of the universe, is the time derivative of the scale factor a dot over a squared. And Einstein field equations tells us that this is related to the overall energy density of the universe, that this is given by a coupling constant, which is either Newton's constant for gravity or the Planck mass, depending on the units you're working in, multiplied by the energy density of the universe. And furthermore, you have a continuity equation that applies to this energy density. The second equation of the dynamics that comes into play here is continuity, in that the time derivative, the rate at which this energy density dilutes with expansion, is given by of course, by the expansion rate, and is also given by the equation of state of the matter, the energy density and the pressure of the matter. So the dynamics of the space-time are determined first by gravity, by the Einstein field equation that tells you how the space-time reacts to the energy density within the space-time. And then it is given by the continuity equation, which tells you how that evolution of the space-time causes the energy density of the matter itself to evolve with time. And so how the dynamics of this universe work, how these equations actually manifest themselves in particular solutions, depends on what kind of matter we fill the universe with. And in cosmology, there are basically 3 classes of cosmological matter that one can consider. The first is non-relativistic matter, which we just refer to as non-relativistic energy density, which we refer to as matter. So this would be any, for example, pressureless dust, or a cloud of particles, or hydrogen atoms, or dark matter particles, or whatever. These, because their number density, as these, for example, if we take a co-moving cube of the universe and let that expand with expansion of the universe, what we find is that the number density of those particles drops as the inverse of the volume of the box. So a co-moving box that's expanding, the energy density inside that box in the particles will just scale as 1 over the cube of the scale factor. And this applies to basically any particle species where the momentum of the particle is much, much less than the mass of it. So any particle that is non-relativistic will obey something close to a matter equation of state. So what we find then, if we plug this into the Robertson-Walker equations, is in the, we know that rho goes like 1 over a cubed. The time derivative of this pressure then goes as the time derivative of the energy density then is equal to minus 3h rho, where that corresponds to then, from the continuity equation, we can see that this corresponds to matter with zero pressure, an equation of state with energy density, but where the pressure vanishes. And if we plug that into the Robertson-Walker equation, so if we take an energy density that goes as 1 over a cubed, it's straightforward to verify that the scale factor evolves as t to the 2/3 power. The scale factor is a power law in time, with the power law for non-relativistic matter being t to the 2/3. The second kind of material that we might fill the universe with is radiation. So an example of this is cosmic microwave background photons, neutrinos, any particle species where the momentum is greater than the mass of the particle. So that applies to massless particles like photons, or for very light particles like neutrinos. Then you have an additional effect that not only does the number density of the particles dilute as 1 over a cubed, but because of cosmological redshift, because these massless particles propagating through the expanding cosmology lose momentum, that means that they increase in wavelength as well and lose energy. So that momentum actually decreases as 1 over the scale factor because of cosmological redshift. And what you find is that then that adds an extra power of the scale factor in the scaling law for the energy density, so that radiation, unlike matter, which goes as 1 over a cubed, radiation, because of this extra effect of cosmological redshift, scales as 1 over the scale factor to the 4th. It drops off more quickly with expansion than matter in the universe. And so we can do a similar trick. We can say that if rho goes as 1 over the scale factor to the 4th, that tells us that rho dot goes as -4 times the expansion rate times the energy density, which then tells us that the corresponding pressure for radiation, or for relativistic matter, is equal to is a factor of 1/3. The pressure is equal to 1/3 the energy density. And so plugging this into the Robertson-Walker equation, then we find that the scale factor goes as the square root of time rather than t to the 2/3. The final piece of the cosmic cocktail that we want to talk about, the 3 basic types of energy density in the universe that we'll be interested in, is vacuum energy. This would be, for example, the cosmological constant, or as we talk about inflation, it will be dominated by a scalar field. This is energy density of empty space itself. So if we just give space some sort of energy density, what we find is that that energy density doesn't scale with expansion at all. If I make the box bigger, there's just more empty space in it. The energy density of vacuum is taken to be a constant. So then if we plug this into the Robertson-Walker equations, first, if we plug it into the continuity equation, rho is equal to a constant has a trivial solution, rho dot is equal to 0. And so from continuity, we then know that this must have negative pressure, that the pressure is equal to the negative of the energy density. This sounds weird, but in fact, there are lots of simple physical systems that obey negative pressure. Negative pressure is just tension, anything where the energy contained in the system increases with expansion, essentially. So a nice example of a system in tension is just a rubber band. As you stretch it, the rubber band tends to restore itself, right? So dark energy is really, maybe a better name for it would be dark tension, in that, in fact, what it means is that it's a system that exhibits tension, and the energy density stays constant with expansion. And if we plug that into if we plug something with constant energy density into the Robertson-Walker equation, what you find is that the expansion rate is constant and the scale factor increases exponentially. And we're going to utilize this not only to explain dark energy in the present universe, but we'll use it to solve a bunch of cosmological problems with inflationary cosmology as we continue. So the current distribution of stuff in the universe is this famous figure that has been put together by lots of painstaking observational work, that the current universe consists of about 73% dark energy, with the remainder being mostly matter degrees of freedom, which is further divided up into baryonic matter, that is atoms, which are about 4% of the universe, and cold dark matter, which represent about 23%. The radiation in the universe today is negligible by energy density. It's about 10 to the minus 4 or so, right, as the total energy density of the universe. But remember that the radiation degrees of freedom in the universe, that is the neutrinos and the cosmic microwave background that are left over from the Big Bang, win by number. They are far more numerous than the dark matter and atoms in the universe. So as we go back into the early universe, because of the different scaling rules for matter and radiation, the numbers win. And if we go back very far in time, in fact, what we find is that when the universe was at a temperature of above about 10 to the 4th Kelvin, the universe was not matter dominated or vacuum dominated. It was in fact radiation dominated. So because of these different scaling laws in the early universe, the radiation wins, and the radiation degrees of freedom are the dominant part of the energy density of cosmology. That happens at a temperature higher than about 10 to the 4th Kelvin, right before matter radiation equality, which happened when the universe was about 60,000 years old. And at about 60,000 years after the Big Bang, the universe went through a transition from radiation domination to matter domination, where in fact it was the dark matter became the dominant part of the energy density of the universe. And that persisted until the universe was around 1 billion years old or so. And after that point, when the temperature of the universe had dropped to around 5 Kelvin, the universe went through a second transition where it transitioned from being matter dominated to being dominated by vacuum energy, or something very much like it, which is the present dark energy in the universe, which is now 73% of the energy density of the universe. We're strongly dominated by vacuum degrees of freedom. So we have this interesting picture of 3 epochs in the history of the universe. So this just gives a quick picture of some significant events in this, starting with the epoch of quantum gravity, grand unification. We don't know what dark matter is or when it formed, but presumably sometime in this very early period before we, at higher energies than we've tested in particle accelerators, is responsible for the formation of dark energy or dark matter. Then the electroweak phase transition, where the Higgs boson underwent spontaneous symmetry breaking, particles acquired mass, bark, bark, woof, woof, all the way down to the universe today, star formation, and so on. And this is sort of the big picture of the history of cosmology that we want to understand. And in particular, when we're talking in these lectures today, when we're talking about inflation, we want to really talk about the question of where did this come from? What was happening back in this very earliest epoch of the evolution of the universe, right? Before the thing that set up the initial conditions for all of this subsequent evolution. This is a curious cosmological model, and it brings to my mind the quote from the King Alfonso of Castile in Spain, who was a great patron of the sciences and the arts and oversaw a community of thriving scientists. He was responsible for the creation of the Alphonsine tables, which was one of the first large collaborations of science in the Renaissance. It was something like 50 astronomers who produced what at the time were the most advanced and accurate cosmic tables at the time, motions of the planets. He said of the Ptolemaic model, if the Lord Almighty had considered me before embarking on creation thus, I should have recommended something simpler. One might say something about this mishmash of different kinds of energy that we have in the Big Bang as well, but it's what we're stuck with, and we have to learn how to explain it. So remember that because of the finite speed of light, we have this light cone structure in our space-time, and what it means is that looking out in space is looking back in time. The further we look back out in space along our past light cone, the further back in time we go, we see things as they were in the past, because in the fact that light took a finite time to get to us, right? We see the sun as it was 8 minutes ago because the light takes 8 minutes to get to us. The consequence of that is because of the finite age of the universe, we can only see a finite patch of it. This is the idea of our horizon, which I'm assuming is also familiar to most of the people in the audience. Don't worry, this starts gentle, but it will ramp up quickly. So that because of the finite size, the finite age of the universe, we can in fact only see a little finite patch of it. If the universe is, when the universe was 1,000 years old, that patch had a radius of about 2,000 light years. When the universe was 5,000 years old, that patch had a radius of about 10,000 light years. That factor of 2, in fact, comes from is an expansion rate. So basically, the size of our horizon is the age of the universe in light years multiplied by an order 1 factor that takes into account expansion effects. And in the case of a radiation-dominated cosmology, that factor is exactly a factor of 2. So as the universe gets older, our cosmic horizon, the distance light can have traveled from us out into the universe, and by symmetry, the distance that we are capable of seeing out, gets larger and larger. And as the universe gets older and older, we see more and more and more of the space-time, more of this infinite space is revealed to us. But at any finite time after the Big Bang, we can only see a finite patch of this. This is our cosmic horizon, or the idea of the observable universe. Now remember, this is an observer-dependent effect, right? So just like two people standing on the surface of the Earth see themselves as having different, each one has their own horizon with them at the center, right? In a cosmological space-time, each observer sees himself at the center of his own local horizon. It's an observer-dependent effect. Everybody sees themselves at the center of their own horizon. So in this way, we all see ourselves at the center of the universe, but that does not break the cosmological principle that we can still have that be true without there being any privileged position in the universe. In these particular solutions, in particular the matter and radiation dominated solutions that we talked about, anytime, in fact, anytime you have a constant equation of state where P is equal to W rho, where W is greater than -1, what you're going to have is that the scale factor evolves as a power law, and you are going to have a finite past age to the universe. And in particular now, we can see that our horizon is just the radius of our light cone projected on this initial surface of the Big Bang. As another way to think of your horizon is that you cut off that light cone, and the horizon is the radius of that past light cone projected on the initial singularity. So I love this plot, which is a quantitatively correct picture of the entire universe. As we look further out in space, we see further back in time. If we look far enough out in space, what we see at our horizon, at the edge of this observable universe, is actually the Big Bang itself. We can't see all the way back because of the fact that the universe was an opaque plasma at the time. But so further and further out, we see further and further back in time. So we see the formation of the first galaxies. We see the first stars, the first structure formation, the cosmic dark ages, the surface of last scattering, where the cosmic microwave background was laid down, further and further back, and we see the Big Bang as a circle surrounding us, with ourselves at the center of the circle. I love this picture because it essentially, what we've done at the end of a century of development of modern cosmology is really, in a sense, recreated the Ptolemaic universe with its prima mobile, the outer sphere of the universe with us at the center. We have exactly the same kind of universe that comes out of Einstein's theory of relativity. Except that it is similar in structure, but different in every detail, of course. And so the result is we have almost this beautiful classical picture of what cosmology looks like. Our current cosmological picture of the universe looks a lot like the universe is seen by the ancients. Now, I want to focus a little bit briefly on this idea, this epoch of recombination, which I know some of the other speakers are talking about, and I won't spend a lot of time rehashing the details. But of course, as we all know, recombination is when the universe went from being ionized and therefore opaque to photons with a short scattering like the photons in a thermal equilibrium gas to electrically neutral. So in the early universe, when the universe was ionized, photons scattered strongly off the free electrons. When the free electrons became bound into atoms, the universe, on a very short time scale, to a good approximation, suddenly went from being opaque to being transparent, and all of those black body photons that were in thermal equilibrium with the baryonic matter at the time began to free stream through the universe and created a background of light, which is essentially the light left over from the Big Bang that we can observe today as the cosmic microwave background. So it's been redshifted by a factor of 1100. The original temperature of the black body when the cosmic microwave background was formed was about 3000 Kelvin. It's been redshifted by a factor of 1100. So the temperature of those photons is now reduced down to a temperature of about 2.7 Kelvin. And this, of course, is the famous Planck image of the anisotropies in that background radiation. It's uniform to 1 part in 10 to the 5th, right? So every direction we look out in the sky, the temperature of the light that we see coming from the surface of last scattering is exactly 2.7 Kelvin, plus or minus fluctuations here that are at the microkelvin level, about 1 part in 100,000. So one unanswered question to the standard cosmology is, how did the CMB get to be so incredibly uniform? This is a big problem because the standard cosmology, radiation dominated or matter domination expansion, not only don't answer this question, they can't, and the reason is causality. In this case, if we are here looking back at the cosmic microwave background, then a photon coming from one direction in the sky in the cosmic microwave background might be coming to us from here. A photon coming from the other direction on the sky in the cosmic microwave background might be coming from over here. And what we find is if we plot the past light cones of these 2 points, they don't overlap. There hasn't been enough time for light to get from one side of from one of these points in the CMB to the other in the history of the universe at the time the CMB photons were emitted, right? So the universe at the time was about 380,000 years old. So the cosmic horizon was somewhere around 300,000 light years or so. So this is actually the sound horizon, not the causal horizon. There are some details there. But basically, if we look at the size of the observable universe as seen by a photon on the surface of last scattering, right, as seen by an atom on the surface of last scattering when it emitted a photon, we see that this cosmic horizon size is about the size of the characteristic size of these hot and cold spots on the cosmic microwave background, or about 1 degree across in the sky as seen by us today. What that means is that there was no way that any of these points were causally connected to each other. There was no way for them to exchange information, exchange photons, and so on. So there's a huge question of how these things got to be in such perfect thermal equilibrium in the first place if they never had any causal contact since the onset of the Big Bang. Enter inflation. So the idea of inflation is that we postulate that in the very early universe, before the cosmic microwave background was formed, quite a long time before the cosmic microwave background was formed in most theories, is that the universe was not actually, so the standard cosmological model has the early universe radiation dominated simply because of the different scaling laws for the different components of the universe. In inflation, we take the idea that the universe had an early vacuum dominated period and was expanding exponentially. The beauty of exponential or any accelerated expansion is that your observable universe, your horizon size, is approximately constant. Let's see, we had somebody raise their hand, so why don't we try answering a question? I'd be happy to take the question now if you like.
Hello, sir.
Hello.
I have a question. So you said in the previous picture, the horizon size you were showing, that is 1 degree along the sky, you said. So
Right.
if we think that suppose each horizon has a center, right? So if we think that 2 centers are very close to each other, and if we think like that, then we will have some overlapping region of horizons. Then we can say that the horizon might be connected to each other.
Well, like in this picture.
Yeah,
Right?
yeah.
Overlap between these two horizons, right?
Yeah.
But that means that only that region of overlap might achieve some sort of small thermal equilibrium, right? But you can't have thermal equilibrium between a point here and a point over here. Those are still causally disconnected from one another, right? So I see what you're getting, that you might have adjacent regions equilibrate, but that thermal equilibrium can't propagate outward at a rate that is sufficient to ensure equilibrium in the whole space-time. Does that make sense?
Yeah, but suppose these circles, the center of these circles are very close to each other, then and then we take it forward, onward. I mean, suppose the squares you have drawn, right? So from the first square, you draw a circle, and then another circle you draw whose center is very close to the previous one, and then you do it till you reach the other circle end. So then you will have a region of connecting regions. So then you can have an exchange of information, and that's
So
what.
yeah, I see what you're talking about, right? So you're saying, so I draw a circle like this, and then I draw another circle like that, and then I draw another circle like that, right? And the point is that you still can't propagate something from here out to here. There's not enough time for it to happen. So no effect from this point can propagate all the way out to that point. even because there's always you can always define those connected horizons, but it's a matter of did the there hasn't been enough time for a causal signal to propagate from this point to this point still.
Okay. Okay. Yeah. I
Right.
get. Thank you.
I hope that helps clear it up a little bit.
Yes. Thank you very much.
Well, maybe I can check whether there are questions here in the lecture hall as well.
Sure.
Are there any questions? Okay, there are none. I just wish to make one remark about the signature. David was using minus plus plus plus.
I am using minus plus 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 as well.
No, your metric was plus minus.
The proper time, well, I was defining the proper time as the proper, ds is the proper time.
Oh,
not the ds squared is equal to minus g mu nu x mu x nu here.
okay. I'm sorry.
I haven't written down a metric yet.
Okay, all right. Thank you.
So I am, I usually use plus minus minus minus, but I know that everyone hates it. So I have, I've like bitten the bullet and I'm using minus plus 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 in my lectures. When we actually do things that depend on the metric signature, it will be a minus plus plus plus. Okay, so where am I? Right. So what we see here is in an accelerating universe, you have the horizon size of the universe, which is given by the inverse of the Hubble parameter, stays approximately constant. But the universe is expanding exponentially quickly, so that then two observers who are initially in causal contact, actually, as the universe expands, because the horizon size doesn't increase in size, but the universe is expanding exponentially, those two observers are stretched outside of causal contact. In this way, we can take an initial patch, right? So now in an accelerating or an inflationary space-time, we can take two observers who are initially in causal contact, can shake hands and agree on things like the temperature of the cosmic microwave background and so on. And then later on, we use accelerating expansion to blow that initial homogeneous patch up to a gigantic size and explain the homogeneity that we see of the universe later on scales larger than the horizon size by a period of early inflationary expansion. This is the basic idea of how inflation solves the horizon problem of the universe. You take a little patch of the universe that is presumably in some sort of approximate thermal equilibrium, and then you stretch it with exponential expansion to arbitrarily large size, and you can explain equilibrium on scales much, much larger than the horizon size by simply introducing a period of accelerating expansion early on in the universe. Similarly, at the same time, and this is a neat hat trick that inflation does, is inflation, this accelerating expansion, not only solves these causal problems of why is the cosmic microwave background so homogeneous, but it also explains why the universe is so close to geometrically flat. We measure in the universe today that the universe is flat to about 1%, which we'll see in the next slide is really is hard to explain because it's an unstable equilibrium. But inflation, basically the picture here is that if I start out with on a curved manifold where my horizon is comparable to the curvature radius, so that what I see is myself in a curved space-time. Later on, if I blow that up exponentially large without changing my horizon size much, what I find is that this accelerated expansion makes my local patch of the universe look flat, just like the Earth, when we stand on it, looks flat because our horizon is so much smaller than the radius of the curvature of the planet. The same thing happens in inflation, where our cosmological horizon becomes much smaller than any potential radius of curvature of the background space-time, and so the universe appears almost exactly flat. So it explains the apparent flatness of the universe. In mathematical terms, we can write this as follows, which is we can take the Robertson-Walker equation. Now, this is the equation of motion for the universe, including the possibility of curvature, where k is equal to +1 is positively curved, k is equal to -1 is negatively curved, and 0 is flat. And we can rewrite this equation simply by writing it like this and defining a parameter omega, which is the energy density divided by 3m Planck squared h squared, which is called the critical density. And that is equal to 1 plus the curvature divided by a time-dependent factor that depends on the expansion, right? So in fact, if the curvature is 0, that tells you that omega is exactly equal to 1. If the curvature is positive, if k is plus 1, then omega is greater than 1. And if k is curvature is negative, then omega is less than 1. So this density parameter omega is a way that we parameterize the curvature of the space-time. So we measure today in the universe that omega is equal to 1 at about the 1% level, or maybe a little bit better. Well, what we find is that in a matter or radiation-dominated universe, so we can write then a dynamical equation for omega, that is omega minus 1 is just given by this 1 over ah squared. In general, it's time dependent. But what we find is that if omega is exactly equal to 1, it stays equal to 1 at all times. But if it's greater than 1, it becomes more curved. And if it's less than 1, it becomes more negatively curved, which means that the flat universe is an unstable equilibrium. As long as the energy density of the universe is greater than negative 1/3, which corresponds from the Ray-Choudhury equation to decelerating expansion, as long as this A double dot is negative, it's an unstable equilibrium and the universe evolves away from flatness. So that means that if the universe is flat to 1% today, it must have been flat to about 1 part in a trillion at primordial nucleosynthesis, an unbelievably fine-tuned situation. So inflation solves this fine-tuning problem by taking an equation of state that's less than minus 1/3, which tells you that the expansion rate of the universe is speeding up, in which case omega is equal to 1 is a stable equilibrium. A curved universe is driven toward flatness. So remarkably, in addition to explaining the causal structure, explaining the causal paradoxes in the Big Bang, the Big Bang contains no explanation of why the cosmic microwave background is in thermal equilibrium. It also explains this apparently highly fine-tuned situation where the universe is almost exactly geometrically flat by introducing a period of accelerating expansion in the early universe that drives the universe toward geometric flatness. So let's look at this on a conformal diagram. So we're going to take, since we now know that the universe is driven toward flatness, we're going to generally assume a flat universe. We're going to ignore this curvature piece, because if inflation goes on for long enough, the universe becomes extraordinarily flat, and we can ignore curvature later on, as long as inflation goes on for enough of a period of time, and consider exponential expansion in the case of this flat universe. So let's transform to conformal time, this clock that slows down with the expansion of the universe, so that the scale factor is an overall conformal factor. And what we find is that, unlike in the case of a matter or radiation dominated universe, in the inflationary universe, in an exponentially expanding universe, that conformal time is negative. And t goes to minus infinity is early times, and the conformal time going to 0 is late time. Right? So in fact, you start with at some very long negative conformal time, and you evolve up to conformal time is equal to 0 at the end of inflation. So on our conformal diagram of the history of the universe, inflation solves the horizon problem by creating essentially a vast sea of conformal time that happened essentially before the moment that we had assigned as the Big Bang. So in an inflationary universe, you get rid of the Big Bang singularity and replace that by the end of inflation. And earlier on in the expansion of the universe, you can have an arbitrarily large amount of negative conformal time, which gives these past light cones, these points in the CMB, time to overlap, and you can explain the homogeneity of the universe. So this is just explaining what I explained before, except now in the language of a conformal diagram, is that inflation gives you a sea of negative conformal time that allows your past light cones to overlap. And this negative conformal time can go on indefinitely long. You can have an enormous amount of it that happens before the end of inflation and the onset of the hot Big Bang. Now notice that I wrote down when I said, okay, we're going to have a period of exponential expansion, and it solves all these problems. We can't do that with a cosmological constant. We can't do that with simply vacuum energy, for the simple reason that inflation has to end. We have to make a transition between this accelerating expansion in the early universe into decelerating expansion, radiation dominated, and a hot thermal equilibrium universe. So in order to construct a model, in order for this to create a boundary condition for our universe that explains the universe that we live in, not only does that vacuum energy have to dominate at early times, but it also has to be dynamic. It has to disappear and decay into all of the particles in the standard model that then heats up the universe and creates the initial conditions for the hot Big Bang. And this decay of this vacuum energy is called reheating. And we won't spend a lot of time talking about reheating in detail, but aside from the fact that it has to happen in some way. So we need to have not just vacuum energy, but some sort of energy for empty space, some sort of vacuum-like energy that is in fact dynamical. And it turns out that particle physics gives us the perfect candidate for this, is symmetry breaking. Now, an intuitive analogy I like to use for symmetry breaking, or better yet, an example of symmetry breaking, is a pencil balanced on its tip, right? If I take a pencil, balance it on its tip, we know what's going to happen to the thing. It's going to fall over, right? But while it is balanced there, classically, this pencil, if we balance it perfectly, should stay there forever. Real pencils don't because of air currents and gravitational effects and Heisenberg uncertainty principle and stuff. But a pencil balanced on its tip has a rotational symmetry. If I rotate that pencil about the vertical, I get essentially the same thing back. So I have a pencil balanced on its tip. It has a rotational symmetry. However, when the pencil falls over, it breaks that symmetry. In order to fall over, that pencil has to pick some direction in space. The direction it picks is arbitrary. It could fall to the left, it could fall to the right, but whatever state that pencil picks when it falls over is no longer symmetric. So we have a symmetric state and a symmetry breaking state. The symmetric state is the pencil balanced on its tip, and a symmetry breaking state is the pencil falling over and picking a direction which no longer has a rotational symmetry. But also notice that the pencil on its tip has potential energy, and the potential energy of the pencil when it's laying on its side is at a minimum, right? So that we have a state where there's high potential energy and low potential energy. So we can plot the potential energy of the pencil as a function of the angle of the tip, and it looks something like this. It's at a maximum when the pencil is sitting on its tip. It's at a minimum when the pencil is sitting on its side on the table, and in between we have some sort of in-between state. Since remember that it's independent of the direction, the pencil can fall over in any direction. This potential itself is rotationally symmetric, and we get this very familiar, to those of you who have studied symmetry breaking, for example, in the Higgs boson, this familiar Mexican hat or sombrero shape of the symmetry breaking potential, which has a maximum when the symmetry is unbroken and a minimum when the symmetry is broken. The neat thing is that this is not just, this sort of idea doesn't apply to just pencils. It applies to any system that undergoes symmetry breaking, ferromagnets, the Higgs boson, grand unification, you name it, any phase transitions in condensed matter and so on. This is a ubiquitous thing, is that the symmetric state will have some sort of energy. The symmetry breaking state will have a lower energy, and therefore the system will tend to evolve from the symmetric to the asymmetric state. So this is the idea of symmetry breaking now, is that we have a pencil that has a symmetric state, but has potential energy maximum. Then it breaks the symmetry by falling into its minimum of its potential, but that means you have to pick out a direction. The symmetry is no longer realized by the vacuum state of the system, and you have symmetry breaking. The only difference now is if we want to consider a field, for example, a field like the Higgs boson, right? That a field is a thing that permeates all of space and time. So a good model, for example, for a Higgs boson or another scalar field is an infinite number of pencils, all balanced on their tip, one at every point in space. And in fact, these things are coupled, right? So they support things like wave phenomena and so on. So when something like the Higgs boson is at the maximum of its potential, when that ball is sitting up on the top of the hill in our abstract picture of symmetry breaking, all of these pencils are lined up on their tips. And when the symmetry is broken, all those pencils fall over and are laying on their side, and they pick out a particular direction in space and break the symmetry, right? So in this case, in the symmetry, in the symmetric state, every one of those pencils carries a little bit of potential energy, right? Or the field in its unbroken state contains a little bit of potential energy. And this potential energy of the Higgs boson, then, since it basically every point in space carries with a little bit of potential energy, this acts exactly like an energy density of empty space. This acts exactly like an effective cosmological constant. That a scalar field in an unbroken symmetry that has some sort of potential energy associated with it acts when you apply it, put it in a relativistic situation, it acts just like a cosmological constant, drives accelerating expansion in exactly the way we want. It creates really an energy density of empty space. It took people a while to realize this, right? The first paper is noting that you could use scalar fields in a symmetric state and use their associated potential energy as an effective cosmological constant was only realized in 1974. And in fact, there were two people who did it simultaneously, one of them in Russia, who was Andrei Linde, who wrote a paper on this in 1974 for JETP. And this was at a time when there was not a lot of communication between US and Russian scientists. So not surprisingly, in the same year, or maybe surprisingly, in the same year, it was also independently discovered by a US physicist, a guy named Joseph Dreitlein, who probably is less familiar to you, who turns out was actually one of my professors at the University of Colorado in Boulder when I was a graduate student. So this was something that was realized in about 1974, which was a few years before Guth actually put it all together to come up with a full theory of inflation. But one thing that is kind of neat about the history here is that this idea of inflation was something that was building gradually over time, over a period of years, in a series of incremental steps. And Guth was the guy who really put them all together into a final picture that allowed you to see how it all fit together and understand it, and as a way to look at a model of early universe cosmology. But many of the ideas that are essential to inflation were kicking around really before Guth came up with his very famous paper. So the idea here then is that we're going to steal this idea of symmetry breaking, which particle physicists stole symmetry breaking from condensed matter physicists. We're going to steal it from the particle physicists, and we're going to use it for cosmology. And what we're going to do is we're going to say this gives us exactly the perfect physical mechanism we need for having a dynamical vacuum energy. Basic idea here then is that we start out during inflation. We have a long period where the Higgs is in its symmetric state. The space has an effective energy density, which during inflation is generally quite large, on the order of 10 to the 15 GeV to the fourth. And at some point near the end of inflation, then the symmetry breaking will occur. The field will drop down to its minimum. At that point, the field is coupled presumably to all of the other particles in the standard model. And when it hits that minimum, it decays into standard model particles, heats the universe up to extraordinarily high temperature, roughly around whatever the energy density of the universe is at the end of inflation. All that energy gets transferred into hot thermal equilibrium standard model particles. And this sets this initial condition for the hot Big Bang. So this is the basic idea of inflationary cosmology. We use symmetry breaking as a dynamical vacuum energy to drive early accelerated expansion, which then ends in a period of reheating and sets the initial conditions, the boundary conditions for the radiation-dominated universe. And this would be a very good time to raise questions and to ask questions. So I see a raised hand. Why don't we take a couple of questions here? We have a lot of time for questions. So I know that the talk is 90 minutes, so we should be able to take a pause and have some discussion here at this point.
Maybe we can request Adil to ask the question first, and then Neilsha.
Sure.
We'll come to Neilsha a little later. Adil, go ahead, please.
Yes, thank you. So, hi, sir. So here in this slide, all the pencils have basically taken one particular direction in basically towards the right, the form. So is that necessary, or basically symmetry can be broken non-uniform?
That's an excellent question, that's at the heart of what's called the Kibble mechanism. So we have a minute, we can talk about that. So the question is, in this picture, I have all of these pencils are falling in the same direction, which seems a little funny, right? If each pencil independently can fall in any direction, you would expect them to just fall. If in real life if you took 50 pencils and stood them up on the table and just let them drop, they would not all do this, right? Of course, the answer is that in a real scalar field theory, these pencils are coupled to each other. Right. So if I look at the Higgs boson now, right, each of these pencils is actually it's a coupled system. A scalar field theory would have these pencils would actually be interacting with each other. So that, for example, a wave propagating through the scalar field, something like a momentum mode that we would interpret as a particle momentum in actual field theory, would be a wave propagating in these coupled pencils. So they would wave back and forth, for example, or something like that, right? So you really, if you want to talk about a scalar field theory, you want to think of these as coupled to each other, so that when one of them falls, the other ones, its neighbors, because of the coupling, tend to fall in the same direction. And so if the symmetry breaking phase transition, so the phase transition will really happen where one pencil goes, and because of its coupling to its neighbors, it will drag its neighbors down with it. And because of that coupling, it and its neighbors will tend to fall in the same direction. If they fall in different directions, that would mean there's an energy in between them. That wouldn't be a minimum energy state because of the coupling energy between the two, right? So because of the coupling, the minimum energy state is all these pencils in the same direction. What you will find, however, remember that this phase transition, when it happens in cosmology, you have horizons. So in fact, this coupling can only propagate within this local patch. These pencils will all fall in the same direction within their own horizon. But pencils outside the horizon, as seen by these guys, will fall in an independent direction because they're causally disconnected. So what you would expect actually is you would have each cosmic horizon would have all the pencils in one direction because of local couplings, but other cosmological horizons, because they're causally disconnected, would fall in a different direction. And then as the horizon grows, these domains of different symmetry breaking, these would be like different domains in a ferromagnet, right? Or in a ferromagnet, you might have all the magnets line up in one direction in one part of the crystal, and all the magnets lined up in another direction in another part of the crystal, right? So this is like domain formation in a ferromagnet, except it happens in cosmological horizons. As the horizon grows, these domains are going to meet up with each other and become causally connected. Then what you're going to find is you're going to have a mismatch, right? It'd be like a crystal defect. So you would have the Higgs boson would break the symmetry one way in one horizon, another way in another horizon. Then you're going to have all these defects where these domains meet up. That's what a topological defect is. That's what a cosmic string is you have symmetry breaking happen in different ways in different horizons. When they all meet up, they form topological defects. This is the mechanism by which you form, for example, cosmic strings in the early universe, or magnetic monopoles, so the form of the topological defect depends on the kind of symmetry breaking, but this is exactly how the Kibble mechanism works, is that these pencils will all fall in the same direction inside their common horizon, but in different horizons, they'll fall in different ones, and this will create these defects, which then will generically result in topological defects in the universe. A nice thing is that if there are any of these topological defects there in the first place, inflation gets rid of them because it stretches you out to a single domain where all the pencils were lined up one way. So even if you have a bunch of domains where the symmetry breaking happens in different ways, they'll be stretched by inflations to so far outside each other's horizons that you'll never see them. So in the inflationary universe, you can just treat it as if all the pencils fall in one direction and you're good. So does that answer the question? That's a very long-winded answer, but it's an interesting question.
Okay, well, Adil is not responding. So I have a question here from the lecture hall.
Sure.
Hello.
Hello.
So you said that how inflation explains this horizon problem is that initially we already have a patch which is in thermal equilibrium. Then they leave each other's horizon. See, after reheating happens, thermal equilibrium is kind of easy to understand because inflaton decays to standard model particles and they scatter off, and you can define a temperature. And rho goes as T to the power 4. But before reheating happens, how do you ascribe a temperature to that?
Well, in fact, before reheating happens, the temperature of the universe is absolute zero, right? So the inflationary period, right? So let's go back to this diagram here, right? So what you find is, okay, so after the end of inflation, you're in a hot thermal equilibrium. Whoops, get back here. After inflation, you're in a hot thermal equilibrium universe, right? But during inflation, during this period, in fact, because the universe is completely empty, right? Anything that was in there beforehand, if there was anything, is driven to zero density by the exponential expansion. So all you have left is this scalar field in a completely coherent state. It's basically the universe is a Bose-Einstein condensate. So you have a zero temperature, completely coherent field on scales larger than your horizon size, in fact, much larger than your horizon size. And this is, it's a zero temperature Bose-Einstein condensate. So the temperature of the universe before reheating is zero.
What did you mean when you,
universe,
sorry,
go ahead.
When you said that we initially start with the patch which is in thermal equilibrium and then it
so now you're asking questions about initial conditions, and you're right, I have cheated. Because in fact, there's no reason to expect the pre-inflationary universe to have been in thermal equilibrium at all, right?
Mhm.
We don't even know. We don't even know what the dimensionality of the pre-inflationary universe was, much less whether or not it was the thermal equilibrium. Early models, like with Goose, it was really a thermal equilibrium phase transition was the way he did this. But of course, subsequently, we realized that there was no reason for a thermal equilibrium in the pre-inflationary universe. So what it does is it creates a causal structure that allows you to create thermal equilibrium, a more accurate way to put it, right? So I cheated in my early explanation because it's intuitive, but many times things that are intuitive turn out to be wrong when you understand them better. And this is a nice case of that. So excellent question. We really don't have any reason to believe that there was thermal equilibrium prior to inflation, but that doesn't matter because we can create this thermal equilibrium in reheating by defining our constant time hypersurfaces to be constant temperature hypersurfaces at the end of inflation, which is one way to define toe-moving gauge. And we will spend a lot of time. We're gonna dive deep into the technical details of this, in particular gauge dependence of this stuff in general relativity, coming up real quick, right? So really what we're doing in a technical sense is we're defining our constant time hypersurfaces to be surfaces where inflation ends simultaneously at all points in space. And that basically we create a foliation of space-time in which the universe is completely homogeneous by construction in general relativity. And I'll show you how that happens going forward. Does that help a little bit? But you're right, what I told you was inconsistent.
Hi, Will. Can you hear me?
Yep.
So
I
in
can
this
hear you.
pencil and diagram analogy, can we also state it like that when the pencil is straight, it is acting like a particle. I mean, they are not casually connected. But when the energy goes down and the pencil actually falls down, they are interacting and they can be treated as inflationary fields. Is that right?
In a sense, yes. I think that's accurate. But what's really driving the inflation is just the energy density of the pencils, not anything to do with the interaction per se, right? So in particular, we're going to be talking about free scalar field theories, so that this is different from interaction in the field theory. And I would caution against pushing this analogy too far, okay? This is to give you an intuitive picture of how energy density changes, not so much to explain the details of how we construct a scalar field theory in this situation.
Okay, and can you also please share the references which paper you were talking about, 1974, which firstly showed this analogy above?
I can get those for you. And I should have, I was planning on noting this at the start. I want to apologize because the references in this talk are a little bit thin, mostly because I didn't have time. And so I'm unfortunately eliding a number of references that I can put together a little bit later, and hopefully I can put up maybe a bibliography of the papers that I'm talking about. But I don't have them in the slides, and I apologize. But mostly it was because I didn't have time to get all that together and get the slides together.
Can you put them on the Slack channel?
Sure. Yeah, I'll put those papers in particular up on the Slack channel for you guys. That's a great idea. I'll do that today after the lectures are over.
Just have one more question here, Will.
Sure.
So my question is about that horizon concept. So I assume that this horizon concept is related to the size of the causal universe. So
that's right. Those are equivalent.
And so then can we say about anything about the actual size of the universe? Is it related to the horizon?
So, okay, looking at, for example, this picture of the cosmological horizon, right? So this is my original diagram of the horizon. So we're standing here, right? Or some observer. And you can only see as far out as essentially 1 over the Hubble constant, right?
Yes.
But now, which means that you can't see this other observer out there. Presumably he's there. There's space out there. The universe is homogeneous and isotropic, so that space out there is pretty much the same as our space, right? So just like, remember, let's back up a little bit further, right? When I was even talking about Minkowski space, when I was talking about the light cone and elsewhere, right? As being, so this sort of like really is a separate universe. It's things that are causally disconnected from you. The thing here is that these points out and elsewhere aren't separated from you by any kind of a horizon. And in particular, then if I take some sort of world line, time-like world line from this point, if I just wait long enough, that thing will that thing will be able to communicate with my causal future. And so some causal future version of myself will actually be able to observe this point that that here was actually in my elsewhere, right? So once I go further up into the future, this thing is within my past light cone and I'm causally connected to it. So in this case, in the case of a Minkowski space, I become causally connected to more and more of the space outside of my light cone as time progresses, right? Well, exactly the same thing happens in a cosmological horizon, except the difference, of course, is that because it's cut off, not only elsewhere, all of these other points that are outside my causal horizon, right, are separated outside of my causal space, are separated from me by a horizon. So now really this, these things here represent, whoops, I want to represent different universes, right? In the sense that I have these two horizons that are completely causally separated. Your question, if I'm remembering it correctly, is what can we say about the overall size of this manifold? How far does this space go on? And the answer is we can't say much of anything, right? We can say that this this universe, what we can say observationally based on data is only that the universe is much, much bigger than our current observable universe. We can't say how much bigger, although we know it has to be a little bit bigger. There are constraints, for example, if it were topologically closed on scales that were a little bit bigger than our current horizon, you'd be able to see that in the cosmic microwave background. Right, so one way you can test this is you can look for repeating patterns in the CMB if the universe is rolled up into a donut in a higher dimension or something like that. And there's no evidence for that. So all we can say is that we know that the universe is a lot bigger than our current horizon. In inflation, if inflation is correct, right, that means the universe is vastly larger than our horizon, right, exponentially so. So in inflationary models, whatever happens, whatever weird things that might happen out at the boundaries are inflated to such large scale that they never become relevant for us. And furthermore, because of dark energy, right, what we find is that in the case of dark energy, now we are dominated by vacuum energy in the current universe. So we're actually living in a universe in which, currently we're living in a universe in which things are inside our horizon are being swept outside of it, which means that our horizon now, or actually a region a little bit bigger than it, right, because we're still in the transition between matter domination and radiation domination. So there's a patch that's a little bit bigger than our current horizon size, which is it. It is all that we will ever be able to see as long as dark energy is sufficiently stable. And that even if we waited into the infinite future, if our future really is a de Sitter limit, we will only be able to see a finite patch of this larger manifold, and the entire rest of this is forever forbidden, right? It really is a different universe. And this is the next sort of more complicated sense of a different universe, is that these regions of my cosmology that are outside my observable universe, I will actually never have access to them. And these represent, in some sense, a real separate universe from ours, because they were never causally connected in the past, and they will never be causally connected in the future. And that's rather weird, right? But the global structure, we have no way of knowing it because we can never access it. Does that help answer your question?
Okay, thank you.
Will, can we take one or two more questions?
Sure, I have about
20 minutes.
I have about 10 more slides to go through in about 15 minutes.
Okay. So maybe.
So do we want to do more questions? Or I would like to get to some of the technical details of this before we wrap up today.
Can we ask this later? Can we take this later? Okay, we will take the remaining questions later, Will. Maybe towards
okay, or maybe we can have long discussions in the tutorial session tomorrow as well, right?
Yeah, please proceed, Will.
Okay. So now let's start getting technical about this. That's the big picture overview, right? So now let's really dive into this. So in fact, the way we want to do this is basically we're going to use spontaneous symmetry breaking as a way to generate this dynamical vacuum energy that we need for inflation, which means we need a scalar field. So let us write down whoops, I'm sorry. Oh, I have more than 9 or 10 slides. Let's take a look at how we write down fluids in general relativity. So I might not make it all the way to the end of my slides today. We'll check these on in the next lecture. So we want to talk about how we take a scalar field and use it to generate stress energy in the universe, right? How do we couple these scalar fields to gravity? And I want to do a bit of a general treatment of it because this will be useful later in some of the more advanced discussions that we're having. We can write the stress energy down for a perfect fluid as the stress energy is equal to the pressure times the metric. So this expression here is a general expression for the stress energy of any perfect fluid, right? It's a tensorial quantity. And here, this u mu u nu is the Four velocity, and particularly the Four velocity of the fluid. So if I have a fluid that is moving through space-time along, every element of the fluid has its own world line, right? Then as long as that fluid doesn't have any vorticity to it, then I can write down a general expression for the stress energy tensor, which is given in terms of the energy density and the pressure of the fluid by this expression, where this u mu is the Four velocity field that's defined by the world lines of the fluid itself. Okay. Now, then there's a natural foliation of the space-time, and this is really the origin of what people call co-moving gauge when they talk about co-moving perturbations, right? And we're going to spend a lot of time talking about what co-moving gauge means and how it works. Is we can so if we have a fluid with where the fluid elements have world lines through the space-times that form what's called a time-like congruence, where they fill the space and they don't run into each other, we can then use that to define a foliation of the space-time, divide the space up into time, which moves along the fluid flow, and hypersurfaces orthogonal to that fluid flow, which we're going to define as spatial surfaces. Okay, so we have a Four velocity field that is time-like, that is defined by our fluid flow, and then we have hypersurfaces that we can foliate that space-time, and hypersurfaces that are everywhere locally orthogonal to the Four velocity. Well, this means that we can rewrite our stress energy tensor as the energy density times a time-like projection operator and the pressure times a space-like projection operator in the following way. The operator that projects a four vector parallel to the fluid flow is just the fluid Four velocity itself, right? So for example, we can define a coordinate invariant version of a time derivative, which is just the derivative with respect to the proper time as seen by the fluid flow itself, which is just the Four gradient operator d mu projected along the direction of the fluid Four velocity, which is u mu. So now we can define a projected time derivative by projecting the Four gradient along our time-like direction, that is along the fluid flow. And similarly, we can define a spatial gradient operator as projecting the Four gradient along space-like hypersurfaces orthogonal to the fluid flow. And it's not hard to work out that the appropriate spatial projection operator is just given by this expression, g mu nu plus u mu u nu, right? So a general tensorial operator. And it's straightforward to show that, for example, this is everywhere orthogonal to the Four velocity, because if we apply this projection operator to the Four velocity vector, it's everywhere 0, right? So we're going to define a coordinate independent notion of time derivative and gradient by either projecting along the fluid for velocity or perpendicular to the fluid for velocity. All right. This is a formalism that was pioneered by Hawking and Ellis. Sorry, was it Hawking and Ellis, or yeah, I think it was Hawking and Ellis. And basically the idea here is that you can write down essentially coordinate independent expressions for time and space derivatives, right? As long as you have any time-like foliation of the space-time, you can define parallel or orthogonal derivatives and define these projections in this way. So let's apply this to scalar fields. If we fill the universe with a scalar field, it is also not hard to show that I can define an effective velocity field associated with that scalar field just by d mu phi divided by this expression involving the metric and the two derivatives, right? So the nice thing about this is that this gives us a time-like 4 vector, which has the correct inner product properties. The time-like 4 vector has everywhere has an inner product equal to -1. See, Sriram, I am using a negative minus plus 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 metric. And so it's straightforward to verify that in this case, all the inner product of this with itself is always equal to -1, and it's always time-like. So this forms an effective 4 velocity field associated with my scalar field. And then I can write a coordinate independent version of the notion of the time derivative of my field is just the time derivative of the field with respect to the proper time along the fluid flow lines, which is given in coordinate notation by the 4 velocity contracted with the gradient operator. Okay, this is what I'm going to mean in a coordinate independent sense by a time derivative. So I have not yet specified a gauge. I haven't specified any particular foliation of the space-time, except that I'm defining my time derivative to be the gradient, the 4 gradient projected along the fluid flow. And I'm defining my spatial derivatives to be the 4 gradient projected orthogonal to the fluid flow. So I am going to, throughout these lectures, be giving sort of inline exercises, stuff that it will be left as proof for the student. So something to do when you go home then is to show, first of all, that if I define my fluid 4 velocity in this way and my time derivative in this way, that this in fact satisfies the correct orthogonality relationship, and that the square of this 4 velocity, the square of this time derivative is in fact the usual, in coordinate notation, is the usual kinetic term that we would assign to a scalar field. So this is a very elegant notation that allows us to write down, for example, scalar field kinetic terms in completely coordinate independent ways that then when we drop down into a coordinate system gives us the usual notion of a scalar field kinetic term in a scalar field theory. Okay. So let's talk about stress energy then. Let's talk about the energy density associated with the scalar field if we give it a potential. Now, those of you who know their field theory in curved spacetime will know that I've cheated a little bit, because a scalar field is only isomorphic to a perfect fluid in the case when it has no potential at all. So we're going to cheat now. We're going to add a potential in, which means it's really no longer a perfect fluid, but as long as it's homogeneous, we can still treat it like a perfect fluid. So a general scalar field is only a perfect fluid when there's no potential at all. A scalar field with a potential can still be treated as a perfect fluid as long as the field is homogeneous. And we're going to be taking a homogeneous approximation going forward. So in fact, we want to assign a pressure and an energy density to our scalar field. That's easy. The energy density of the field is just the Hamiltonian density. So if we take the kinetic energy of the field, add the potential energy of the field in, that just gives us the energy density of the field in space-time, right? And furthermore, the pressure of the field is just given by the Lagrangian. It's a nice fact of scalar field theories that the Lagrangian is just equal to the pressure. So we have natural definitions of pressure and energy density for the scalar field. And as an exercise, we can show that if we take a foliation of the space-time, if we pick a particular foliation of the space-time such that in coordinate notation, the scalar field for velocity is everywhere time-like, that is just equal to 1, 0, 0, 0, and the gradient of the scalar field is negative, then the stress energy tensor can be written down in this familiar form, which is P rho 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 rho, or rho P P P P, right? So we can write down for if we take this arbitrary scalar field and we foliate the space-time such that it's always orthogonal to the fluid 4 velocity, that foliation guarantees that the scalar field will be homogeneous in that coordinate system, and we have the perfect fluid stress energy tensor that we need. So the trick that we're doing here is that in a general coordinate system, this isn't going to act like a perfect fluid, but in a co-moving coordinate system, one that's defined where the hypersurface, the spacetime is foliated orthogonal to the fluid flow, it acts exactly like a perfect fluid. And we can apply the perfect fluid stress energy tensor to it, right? And in fact, so we can write in this coordinate system, we can take this and show that the stress energy tensor is exactly equal to this diagonal form where the pressure is given by the Lagrangian and the energy density is given by the pressure. And I leave that one as well as an exercise to the student to show that that is true. So now let's look at the equation of motion for the inflaton field. And what we get is we have a stress energy tensor that is defined in the general form, where I've defined my pressure here is my Hamiltonian and my energy density, my pressure is my Lagrangian and my energy density is my Hamiltonian. Then taking covariant conservation of the stress energy tensor gives me a continuity equation and an Euler-Lagrange equation. And in particular, we're going to, since we're taking homogeneous field configurations, we're going to be particularly interested in the continuity equation. Where notice in this continuity equation, we have this 4 divergence of the 4 velocity field. And it is also straightforward to show that if I take a Robertson-Walker metric, a diagonal metric with the spatial components being a squared, if I take the divergence of the 4 velocity field, that's just equal to -3 a dot over a is equal to -3 times the Hubble parameter, right? So the Hubble parameter really in a cosmology that's full of a uniform perfect fluid is really what you're measuring there is you're measuring the divergence of the 4 velocity field from one hypersurface to another. And we can write then, if we write the pressure and the energy density in terms of the kinetic term and the potential term for the scalar field, remember these are still coordinate independent notions of these things. They become coordinate dependent in the usual, we get the usual coordinate dependent expressions if we specialize to co-moving gauge. We then end up with an equation of motion of the scalar field that looks like this, which is just basically taking this continuity equation and plugging the particular form of the scalar field pressure and energy density into it, right? So continuity tells us that we're going to have this equation that those of you who have worked on inflationary cosmology before, scalar fields in cosmology, will be very familiar with. Phi double dot plus 3h phi dot plus the derivative of phi is equal to 0. That's the background equation of motion for our scalar field in an expanding space-time. Okay. So now that we've constructed a general equation, right, and we're still working essentially in a coordinate independent notation here, right? Although once again, it's coordinate dependent and becomes the usual expressions if you specialize to co-moving gauge. We can then take an approximation such that we are dominated by vacuum energy, right? That's what we want, is in order to drive accelerated expansion, we have to be sitting up near the top of this potential with very little kinetic energy. So most of the energy density we have is vacuum energy. So we'll take the approximation here that the kinetic term is small. And this, of course, gives us exactly the equation of state that we're looking for. This gives us P is equal to minus rho. It acts like an effective cosmological constant. And we are going to drive accelerating expansion. So as long as we're in this slowly rolling regime where the potential dominates over the kinetic energy, we are the scalar field that acts like an effective vacuum energy, and we will drive inflationary expansion. In terms of the equations of motion, that means that we can extend this approximation to say that this kinetic term is going to be subdominant in the Friedmann equation, and the second derivative is going to be subdominant in the continuity equation. And therefore, we have a particular solution to this called the slow roll solution, which it turns out is a dynamical attractor in which the scalar field velocity is just given by the derivative of the potential divided by the expansion rate, and the Hubble parameter is just given by the potential at that given time. So this is the origin of the familiar slow roll solution, which is this attractor solution for inflation, is that we simply take the kinetic term to be subdominant. We're dominated by potential energy. We have an effective vacuum equation of state, and we can drive accelerated expansion. Okay. So maybe this would be a good time to take one or two final questions before we wrap up. And next time we'll start to talk about constructing particular solutions to this, and we will be moving, do an example, a simple example of how we construct an inflationary potential and accomplish a slow roll solution. And then we're going to be moving very quickly into perturbation theory, which I assume most of you are more interested in than a lot of this background material that, at least from talking to Sriram, I know that many of you are already familiar with.
Thank you, Will. We'll take a couple of questions from the lecture hall before we see whether there are questions from the audience and the online. Please go ahead.
Sure. I can stay around as long as you want. If we want to run over, that's great by me. But
So we can take a few more minutes because we are meeting David at 30 minutes later. So we can run over a few 5-10 minutes and then we'll see. Yeah, please go ahead.
Yeah, hi.
Let's take a couple of questions then.
Sure.
Right. So I earlier wanted to ask that what triggers this symmetry breaking process? Like, is it completely random or there are factors affecting it?
Well, it's an unstable equilibrium, right? So you think about balancing a pencil on its tip again, right? So what triggers a pencil to fall over from its tip? And if you put it on the table, it happens really rapidly, right? And you could probably calculate the lifetime of that. So what makes a pencil fall over might be air currents, right? Might be vibrations in the table. Could be, even if those were missing, right? So let's do a highly idealized situation where you have this pencil sitting up there and it's in a perfect vacuum and there's no vibrations. Still, gravitational effects from nearby objects would be enough to eventually pull it over, or even more so, just Heisenberg uncertainty principle. Even if I got rid of all external influences because of quantum uncertainty, that thing's going to jitter around a little bit because of 0-point fluctuations quantum mechanically. And you could use, it's kind of a nice exercise actually, to use the Heisenberg uncertainty principle to estimate the lifetime of a pencil balanced on its tip. That's a pretty classic problem in quantum mechanics, right? So in the case of spontaneous symmetry breaking, what's really going on here is that this is unstable because of 0-point fluctuations due to quantum mechanics. So even if you find a situation where this thing is perfectly isolated from its environment, which is probably a good bet in inflationary cosmology, you still have quantum fluctuations that are going to drive that thing off the maximum, and you can calculate the lifetime of that maximum from applying the Heisenberg uncertainty principle. We will go through that calculation, if all goes well, in the last lecture of this series. We'll actually talk about lifetimes of these unstable states due to quantum fluctuations.
Thank you.
I had a
Another
question.
good question. You guys are asking great questions.
So I had a question before I'll hand it over to a participant. Now, for inflationary potentials, you don't really require symmetry breaking, isn't it?
That is a fact, and we'll talk about that coming up. That's right. So the potential does not necessarily have this nice symmetry breaking shape. It might well have just a bowl shape. And then in that case, you can drive inflation just by being displaced from the minimum, right? So I use symmetry breaking as an example, but you have in chaotic inflation, you also have the case where there is no symmetry breaking, where the symmetric state is a minimum. That would be like a pendulum, right? So this would be something where in fact the symmetric state is a stable state. But if I take a pendulum and displace it from its minimum, then it will evolve down toward that minimum. And I can actually accomplish slow roll in that case as well. So an analogy for chaotic inflation would be a pendulum instead of a pencil.
I understand. Thank you. We have one more question from the lecture.
Hi, Will. My question is just that why do we require slow roll? Is it, without slow roll, would we not have inflation?
No. In fact, we're going to spend a whole lecture talking about non-slow roll inflationary models. Okay. Because those are really relevant to a lot of modern research, right? There are a lot of people doing stuff with non-slow roll models. In particular, they turn out to be extremely useful as a mechanism for formation of primordial black holes. That's one of the reasons why I want to get to these exotic models with you guys, is because it's really relevant to a lot of modern research, is that these non-slow roll models are perfect candidates for forming a background of primordial black holes, which can be an explanation for the dark matter in the universe, for example. So no, we don't have to have slow roll, but you have to have something like slow roll, because remember, you have to inflate for long enough. So this unstable state has to be long-lived enough for you to generate sufficient inflationary expansion. And we'll go through a calculation of how much expansion you need. It's about 60 e-folds, about a factor of 10 to the 24th, at least, in order to explain the horizon and flatness problems, right? So now if you look at this equation of motion for the scalar field, right, you look at this here, basically you have a standard second derivative term, you have the field gradient, but here you have in the center term in the middle is a drag term, right? So the way in inflation that you make sure that this period of inflation goes on for a really long time is you want to have your dynamics dominated by the drag rather than by the slope of the potential, right? So you want this drag term to dominate over the slope term, basically. That ensures that inflation has a really long lifetime. And that's basically the origin of the slow roll approximation, is that as soon as you're dominated by expansion drag, this thing is really, so instead of a pencil falling over, it's like a pencil falling over inside a jar of molasses. And so if I take a real pencil and I knock it over, it goes boom, right? But if I have a pencil inside a viscous fluid that has a lot of drag to it, it will really slowly fall over. And as long as it's in that state where it's still slowly falling over, it will drive acceleration. So slow roll or something like it is necessary in order to generate, is generally necessary in order to generate sufficient inflation to explain all these cosmological problems. But we will talk about cases where the slow roll approximation in the formal sense, right, where this actually breaks down. And we no longer have a complete slow roll situation, and we no longer have this nice attractor solution, and the solutions have a completely different set of dynamics. And that's the third lecture of the series is going to be a detailed treatment of that case where these slow roll solutions break down.
We have one more question from the lecture hall.
So you talked about this flatness problem. So I was thinking whether we know that this omega curvature, inflation drives this omega curvature close to zero during this expansion. So is this scenario observationally any different than if k is very small? I mean, omega curvature being very small and k being very small, are they can they be observationally distinguished?
Well, if there aren't any, perhaps we can wrap it up for today. And I will see you guys first thing tomorrow morning.
Will, there is just one more question. Can you hear us? Well, there seems to be. This seems doesn't.
Oh, we have another one.
Will, there is one more question. Can you hear us? Can you hear us? Gopi, Nabi, Narun? Is anyone there? Gopi, we are not able to. Will is not able to hear us.
Sriram?
Yeah.
I'm not hearing anything. You're trying to get some audio through to me.
Can you hear us, Will?
I'm not getting any audio.
Just.
I'm still not getting any audio. Check mine locally. I think it's working.
Yes, Gopi, there is a problem. Sorry? To hear us. Hi, Bill. Can you hear us?
Still can't hear anything.
I don't know whether he can see us.
Wait a minute. I think the problem is with me.
Hello. Professor, can you hear me?
Oh, yeah, now I can hear you. Sorry. I had a problem on my end.
Can you hear us now, Will?
I can hear you now. Thank
Okay.
you.
Okay. Just one question from the lecture hall, Will. Okay, maybe after this question, we'll wrap up for today.
Okay.
So you talked about this in how inflation drives omega curvature close to zero, that is
Right.
make it flat. So I was thinking whether this scenario is observationally any different than k being very small. I mean, can we observationally distinguish between these two scenarios, that k is very small or omega curvature is very small?
Let me go back to that slide. They're the same thing in a sense, although there's a convention here that's important. Let me bring up that slide with curvature. Where is it? Right, here we go. So you're asking about this here, right? So there are two ways you can do this, right? This is in the Robertson-Walker equation. I can either make k a real number, and k can be anything, right? So k could be -1, 0, +1, 50, -5,000, whatever. Or it's physically equivalent to say that k can only take three values, plus or minus 1 and 0, and that gets absorbed into an overall scaling of the scale factor, right? So in fact, the convention is that k is an integer. K can only be 0 or plus or minus 1, and then that scaling goes into a scaling of the scale factor. So the answer is you can't take small k by definition because k is an integer value. It just tells you the sign of the curvature, and the radius of the curvature is determined then by the scale factor. The scale factor is physically interpreted as being the radius of the curvature of the space-time. So in a positively curved space-time, you're the surface of a four-sphere, right? You're the three-dimensional surface of a four-dimensional sphere. For k is equal to +1, that means the scale factor is then the radius of that sphere. And similarly, in a hyperbolic universe, there's an analog. In the case of the k is equal to 0 case, you're conformally, all the flat spaces are conformally equivalent to one another, so you can rescale the scale factor, and it's just a conformal change to your space-time, right? So the answer is no, that k can't be small by definition because you're defining a to be the radius of curvature of the space-time.
Thank you, Will. There are, I noticed there are one or two raised hands in the people attending online.
I can keep going if you guys want to. I'll stay here as long as you want me to.
The only thing is that we need to meet David in a few minutes. Maybe we can take one question from Neil Shaw. Neil, are you?
Anything else, we can just like save it for the tutorial session. We'll have plenty of time then.
Yes, maybe we can do that if it is fine with you.
Fine with me.
Okay, all right. So in which case we'll close for today. Neil, we'll take your question in the tutorial session or one of the later lectures. Okay. Yeah. And I noticed there are a few other questions from the online participants. We will take those questions in due course of time. Thank you. Thank you for joining us, Will. Okay, we'll see you tomorrow.
Thank you. I will see you tomorrow morning. Have a great day.
Yeah. Thank you.